Okay, so last time in the last lecture, we were discussing about different data types that are used in database management systems and in programming languages. So those data types were primitive data types, okay? That means that they are like used from the very start. And now we're going to see some data structures. So what is the difference between like data structures and those data types which we talked about. So basically, data structure are also used to store data, but it is a specialized format. Okay, they look very different from the data types. So therefore, like used for organizing, storing, and managing data in a computer so that it can be accessed and used efficiently, much like data types, but they look a little bit different. So they're the basically fundamental building blocks in computer science and software engineering. They're used to arrange data in a way that simplifies processing and allows for effective use of associated algorithms. Now, I told you what algorithms are. They are basically step-by-step instructions, okay, which we give to the computer on to perform a certain task. So frame the organization of information so that machines and humans can better understand it. Okay, so in basically computer science and computer programming, different programming languages, data structure might be selected or designed to store data for the purpose of using it with various algorithms commonly known as DSA. DSA is a subject, it's a course basically known as data structure and algorithms, like how basically he's trying to say what it means that how we use data structures to create algorithms for the computer and for programming purposes so that basically computers can understand. Okay, so why are data structures important? So they are important because the primitive data types which we studied in the last lecture, like the base data types, okay, which are integers, floating point values, boolean character, varchar, everything which we studied, they are available in most computer programming languages like Python, C++, Java, and in SQL, the structured query language. But they are generally insufficient to capture the logical intent for data processing and use. Okay, so we're going to see like how these data structures, which we will see their types, how they differ. Okay, so data structures bring together the data elements in a logical way. Okay, that means that basically you apply logic to these data structures, whichever you want to use, and to facilitate the effective use of them, persistence and sharing of data. So they provide a model, a formal model that describes the way the data elements are organized. Okay, so basically, an example of an abstract data type, that means those data types which you have studied in the last lecture, is a customer name. Okay, now a customer name is a what? It's a string. It's a bunch of text. Okay, so that will be stored in which data type? It will be stored in the text data type or in the string data type. So it's composed of what? Character strings for first name, middle name, and last name. Similarly, if you want to store like the age of a person, you will store in integer because age is a whole number. So, what are the factors to consider when choosing a data structure? So, there are 5 factors to consider when picking a data structure. First of all, you need to answer what kind of information will be stored. Okay, so for example, you are making like a web application or a mobile application. So, in that case, you will be mostly using the data structures like arrays. We will see them, okay, in a little while. So, what you need to answer, what kind of information will I be storing? So if you answer that, then you will know like what data structure will I be using. So how will that information be used? Like how is it going to be used? Is it going to be used by a lot of people? Is it going to be just used by me? Like in what context? And where should data persist or be kept after it's created? Like after you have created the data, where should you keep it? Should you keep it in the database management system or should you keep it somewhere else? And what is the best way to organize the data? Okay, and next, for aspects of memory and storage reservation management should be considered. Like obviously, whenever you store data in the computer or whenever you are creating an application or using a database management system, you will always be storing data in the memory and like the storage. Okay, so the storage in our computer is different, the memory is different. Okay, so data, like how data is processed, we all know how data and instructions are processed in our computers, right? So how will that data, where will it be being stored? So how are data structures used? So data structures are used to implement the physical forms of abstract data types, like all of the those data types which we studied. So they are a crucial part of designing efficient software. So for example, this like Microsoft Edge software, which you see on which I am, or which I have opened this PDF right now, it's a software, right? This Zoom that we are having this meeting on, it's also a software. So for designing these efficient softwares, these big scale softwares, which everybody in the world is going to use, for example, they will always be having some sort of data structures behind the scenes. Okay, that does not mean that you're not going to use those data types like integer or float. You will be using them, but you will be most working with data structures. So they also play a critical role in algorithm design, like how the computer scientists, the software engineers design algorithms, okay, how those algorithms are used within computer programs. So today, many programming languages include an extensive collection of built-in data structures to organize code and information. Okay, that means that all of the programming languages which I keep taking names of, like Python, Java, or C++, they all have built-in data structures. So that means you just use them like and you don't have to import them or anything else like that. They are built in your code. Okay, so for example, Python lists and dictionaries are related to Python language, and JavaScript has arrays. Okay, so basically every programming language like Python, JavaScript, or Java, C++ or C Sharp has their own data structures. Okay, so for example, lists and dictionaries exist in Python, but they do not exist in JavaScript. In JavaScript we only have arrays. Okay, we have arrays, we have other data structures. We don't use the lists and dictionaries. Okay, and objects are common coding structures used for storing and retrieving information. Okay, so software engineers, they use algorithms, they use step-by-step instructions that are tightly coupled with the data structures, such as lists, queries, and mappings. These are basically the names of data structures, okay, from one set of values to another. So first of all, if we see the example of how data structures are used before moving on to types of those names of data structures. First of all, stores data. So data structures are used for like storing any kind of data. For example, you want to store a bunch of values, you want to store characters in an array, for example. We will see what an array is. So this is basically the main you can say function of data structures. Then they are used for managing resources and services. So basically, core operating system resources and services are enabled using data structures, such as linked list for memory allocation. Okay, how we will see that, like how what is a linked list, how it's like what is the working behind a linked list, how does it work. And memory allocation means, like for example, you are storing something in the memory, you are allocating memory to a specific part in the operating system. So behind the scenes, linked lists are in use. Okay, then file directory management and file structure trees, as well as process scheduling queues. Okay, these all are different names of data structures. And then for data exchange, how data structures are used in data exchange. So data structures define the organization of information shared between applications such as TCP/IP package. TCP/IP means transmission control protocol and internet protocol. These are basically some protocols that work in the networking layer, the OSI model. Okay, they basically are responsible for transferring packets, network packets to your device. Okay, then next is ordering and sorting. So data structures such as binary search trees, this is also a data structure, also known as an ordered or sorted binary tree, provide efficient methods of sorting objects. Like for example, you want to sort some data, you want to sort your objects such as character strings used as tags. So you will use which one of the data structure you will use a binary search tree. Then for indexing, even more sophisticated data structures such as B trees or binary trees, also these are called as binary trees or B trees. They are used to index objects, okay, such as those stored in a database. Then for searching, we use indexes created using binary search trees, B trees, or hash tables. They speed the ability to find a specific sort after item. Then for scalability, last one is scalability. So big data applications use data structures for allocating and managing data storage across distributed storage locations. Okay, that means that those storage locations are not in just, let's say, one country, they are across different continents. Okay, some storage locations might be in the USA, for example, or in some European countries. Okay, so they ensure scalability and performance. And certain big data programming environments such as Apache Spark provide data structures that mirror the underlying structure of database records to simplify querying. Okay, now if we see the common applications of data structures, like data structures are used in nearly every software system, where first of all the databases. Okay, you will use them in when you are making a query, okay, when you are creating queries in using structured query language, okay, to organize and store records for efficient retrieval. Then in operating systems to manage memory, to for the memory allocation, okay, file scheduling, process scheduling, okay. Then in networking to structure information for data exchange like TCP/IP packets, and in AI machine learning to represent knowledge and information for complex problem solving. Okay, so this is basically like the whole informatory introductory part of the data structures. Now, if you see this image here, we have divided data structures into two types. Okay, that like the data structures are they have two types. First of all is the primitive, and the second one is the non-primitive. So primitive ones, like we studied all of this if you remember. Okay, we just did not discuss the pointer one. The pointer is basically, it's also a data type, but it's mostly like it's not really used like nowadays in programming languages. Okay, but if we are like since we our subject is database, so it's not like relevant into database. Okay, but these are the primitive data types like integer, character, boolean, float. You will see all of them in all of the programming languages. If we talk about non-primitive data structures, so non-primitive data structures mean that they are just like primitive. What does primitive mean? Primitive means old, right? So that means like they are very old. They have been in use for like so many years. But non-primitive, they just the programmers, the developers, they just develop these data structures for use. So they are divided into two types: linear and non-linear. Linear means that they are divided into static and dynamic. We will see what they are one by one. And then non-linear means tree and graph. Okay, so first of all, if you see the primitive data structures, they we have already discussed them, all of these, like character, byte, float, int, all of these, they are used in different programming languages. They are the basic building blocks of data manipulation. Okay, so they're not going anywhere, and they will not ever be outsourced, something like that. Okay, so they're used in different programming languages and in most database systems and SQL. Okay, and if we talk about non-primitive data structures, these are like the main this is the main thing for today. So moving beyond the basics, non-primitive data structures offer more sophisticated ways to organize and store data. Okay, you, for example, you want to go one step further to organize and store data, so you will use the non-primitive data structures. So they are divided into two categories. First one is the linear, and second one is non-linear. So linear data structures, they arrange data in a sequential manner. Okay, sequential manner means that in a sequence. Okay, for example, like there, if we start counting from 0 and go up to 10, and I ask you to write it, write the numbers in ascending order. So what you will do, you will write those numbers starting from 0, then 1, 2, 3, and you will go up to 10. So this is what it means by like it, the data is basically moves sequentially, okay, one by one. And they're classified into two types: static and dynamic. So first one, if you see the static linear data structure type, so that means the size and structure of static data structures are fixed. Okay, what does it mean? Like the size, for example, if you want to have a size of 100, okay, so the size will be fixed. Okay, it cannot be changed. If you try to change it, you will get an error. Okay, and it is predetermined at compile time. That means that before compilation, before running of the program, before your program starts executing, okay, before you try to execute, you will fix the size of this static data structure, and you cannot change it at compile time. If you try to change it, you will get an error. So it has only one like static data structure type. This is array. Okay, so basically it looks something like this. Okay, so this is the array data structure, and how it works and what it is a fundamental linear data structure, okay, that stores a collection of elements of same data type. Okay, now what does this mean? We have learned about data types different, right? Integer, float, value. So suppose you want to store values like this, okay, but you want to store them of the integer. Okay, you want to use this integer data type, or you want to store values, suppose, of boolean data type. So all of the values should be boolean, all of the values should be integer. Now what you will do, you will use the array data type. Okay, sorry, array data structure for this. So array data structure has a fixed size. Okay, and it is basically used to store elements of same data type. Okay, for example, character, etc., etc., in contiguous memory locations. Okay, So each element is identified by a numerical index, which typically starts from 0. That means that its index starts from 0, allowing for direct and efficient access to any element. Okay. Now what does this mean? Like if you look at this diagram here, okay, so that means that this is basically how array looks. Okay, this is how array looks. It looks something like this, and it means that whatever data that you store here in the array, okay, it is stored in contiguous memory locations. Okay, like there are different memories. Suppose this is a memory. Okay, this is a memory here, and these are different like locations. So your first array like will be stored here, then second one here, third one here, and so on and so forth. Okay, so what does it mean? Like this is basically the index, okay? And remember that the array index always starts from 0. Okay, it does not start from 1, it always starts from whole number. It starts from 0. So you will go from 0, and if you want to have the size of array such as 6, okay? You want to have the size as 6. So you will basically make the size fixed as 6, okay? And you will start from 0 and then you will go up to 5. So 0, 1, 2, 3, 4, 5, these are total 6 numbers, right? So in these are basically the values, the array elements, which we call them, okay, or array values. And they are of, if you basically like look at these numbers, they are whole numbers or natural numbers. Okay, so that means they're of the same data type. These are what? Integers. Okay, these are what? Integers. If you wanted to store, let's say, characters, suppose, okay, or boolean values, so you would always like store them in array, but like array is for the same data type. Okay, so and this is how it array looks in if you visualize it, and this is how it works. So for example, you wanted to access the like this number here, 4 here. So how would you access? You will be using the array index. Okay, you will basically use the array index to access this value which is stored in this index. So at 0 index, 2 values stored, at 1 index 4 is stored, and then so on and so forth. Okay, so next one is the dynamic data structures. So dynamic means that they are flexible. Okay, that means that unlike arrays, like arrays are the fixed size, right? But the dynamic data structures, they are flexible. Okay, and they can grow and shrink during runtime. Runtime means that when you are executing your program, they can basically and they can basically be able to grow and shrink. You can change their size unlike arrays. So first one, in the dynamic data structure, you have the linked list. Okay, so what's a linked list? It's a linear data structure that consists of a sequence of elements called nodes. Okay, it has also elements which are called what? Nodes. Okay, which are not necessarily stored in contiguous memory locations. Okay, so this is the difference between array and linked list. The arrays elements were stored in contiguous memory locations, but linked list, the elements in linked list, they are not stored in contiguous memory locations, and those elements are called as nodes. We always use this word for them. So that means that each node contains two parts, the data and a pointer or reference, okay, to the next node in the sequence. So it looks something like this. Okay, this is what like how a linked list looks like. And remember that I have not included the types of each of these data structures. Like they all have their own types. There are like two types of arrays, one dimensional and two dimensional. Then there are three or more types for linked list, and other for stacks and queries as well. Okay, but the main point here is to understand like how these work. So this is the total, like the head, okay, this whole, and in this head basically you have the this is your node, okay, and the first basically node is called head. Okay, first node of the linked list is called what? Head. And in the node you have the data part in which you will store the data. Suppose this is a character a you wanted to store, or a number, suppose 123. Okay, you could store it in the data part, and then the next this is basically the next part. It's called a pointer or reference. It references, it points to the next node. Okay, that is why it's called a pointer. Okay, the next is a pointer, a reference. It points to the next node in the linked list. So this is yet the data part, okay, and then this one is the next node, the pointer reference, okay, and then last one, this is like in the linked list, in the last linked list, basically this part here, Okay, this next part here, it will be null. Okay, if there is no other linked list after this one, it will be null always. Okay, but this data part will always contain data. Okay, this is how linked list work like, but their implementation in coding languages, it's quite a little difficult, and it's a different from other data types. Okay, so next one is stack. Stack is basically works on the last in first out principle. We also call this LIFO. Okay, last in first out LIFO principle. It's also a linear data structure. So that means that the last basically, okay, if you look here, we have three elements. Okay, A, B, and C. So the last one which you are going to push is basically it's a stack command. Okay, like you are going to push another element. Okay, C. So this is the last one. Okay, you push the last element C into the stack. This is how stack basically looks like. So this is basically your top element. At the top of the stack you have the C, then B, and then A is at the last. Okay, so how does it work? Like LIFO principle, last in first out. That means that C will be the first one to come out. Okay, if you were going to remove suppose B, okay, you would have to first remove C, and then you would remove B, and then A, and so on and so forth. Okay, so this is how stack looks like, and this is its principle, last in first out. The last in will be the first one to come out. Remember it like this. Okay, this means the last element added to the stack is the first one to be removed always. Okay, much like a pile of plates or a stack of books. So for example, there are five plates which you have put on top of each other. Okay, so you will obviously, the last one which you put on the top will be the first one to come out, will be the first one that you will take out. The next is Qui. Qui is also a linear data structure. It follows the first in first out principle. We call this the FIFO principle. Okay, so it's like a bunch of people waiting in line for a service, like at a bank, for example. So how does it work? So this is like, imagine these are people. Okay, these all are people waiting in line at the bank. So for the first one to go, okay, at the counter to do some work will be the first one to come out, obviously, because like this is the purpose of FIFO principle. Okay, first one to go in will be the first one to come out. Okay, and if you look at it here, nq means basically it's also a quick command to basically enter the values. Okay, suppose you wanted to enter 9 here, so 9 would be entered here like this. Okay, this is the front or head of the qui basically. Okay, this part, and then this is basically the back or tail or rear. Okay, rear part of the qui, and the first one in will be the first one to come out. So that means if you were to think of it like this, that how 3 came to be here and why is it dequy. Dequy means to basically remove this object here. So that means that you first entered 2, okay, in the queue, then you entered 3, then you entered 4, then you entered 5, then 6, then 7, then 8, and then 9. Okay, so that means that 2 was the first one to enter. 2 was the first one to come into the queue. So it will be the first one to come out. Okay, so this is how the FIFO principle in queue works. Next is the non-linear data structures. So we discussed linear data structures which follow sequential order. Okay, if you look at all of these data structures, queue and stack and array and linked list, they all uh, work on sequential manner. Okay, so next one is the non-linear data structures. Non-linear data structures mean that basically they don't work in sequential manner. Okay, so you can basically allow the data to be stored in a non-sequential manner, facilitating quick retrieval and linkage based on relationships. So for example, if you wanted to, let's say, take out 5 from here, okay, in the case of we, you wanted to take out 5. First, you would have to take out 2, 3, and 4. Then you will be able to take out 5. You cannot just directly reach out for 5 and then remove this. Okay, you will first remove all of the other elements in a sequential manner, then you will go to 5 and remove it. This is in the case of linear data structures, but in the case of non-linear data structures, you would just like remove 5, and the rest of the elements, the rest of the values would be in their place. Okay, So if we look at the types of nonlinear data structures, we have the tree type. First one is the tree. So tree, it looks something like this. Okay. Like how actually like a tree is. It has branches, it has roots. Okay. It has leaves. So this is all the keywords that we use for the tree data structure. The height of the tree. Okay. The root. Okay. The key leaf nodes. Okay. So what does like tree mean? A tree data structure is a nonlinear hierarchical way to organize data elements. Okay, and those elements are called nodes, like linked list. Okay, those elements are called nodes that are connected by links called edges. Okay, now what does this mean? This line here, which is connecting two nodes here, A node and C node. Okay, these are nodes. All of these are nodes. B's are nodes, D's are node, all of these are nodes. Think of them as leaves. Okay, like leaves on a tree. So how are leaves connected to trees? Through branches, right? So this edge here, think of it as a branch connecting these two leaves, A and C. But in like data structure terms, A and C, G, F, all of these like are what nodes? They are elements. They are called nodes. And this linking like line here, which is connecting two nodes, this is called edge. Okay. So next, trees are utilized in various applications, okay, such as file system, organization, okay, database indexing, networking algorithms. So they have like various uses, and they're very efficient for searching, sorting, and data organization, okay, in computer science. That is why these data structures are most used. Whenever like by software engineers whenever they want to create something. Okay, so this is how a tree data structure looks like. Okay, next one is graph. So if we like think about the graph word, what like comes into our mind? If we look at this word graph, we might think of it something like the graph we used to plot the coordinate systems, okay, in maths. But in the case of data structure, a graph looks something like this. Okay, so it's like similar to these circles. These are nodes basically, and these connecting lines here, these one are edges. Okay, so a graph data structure is a nonlinear model of interconnected entities. Okay, that means interconnected vertices. Those vertices are called nodes. You can call them nodes, you can call them vertices, it's up to you. So they represent objects, okay, and edges or links. Okay, so vertices here, okay, two vertices here are connected through edges or links. Okay, they represent relationships between them. So it is used to map real world networks like social connections. Okay, so if you have seen like some I don't know documentary about, for example, let's say ethical hacking, okay, or you might have seen movies like how, for example, in like military movies, in sort of military sense, like how they are using like this person is here, this is his location, okay, and he is basically connecting with this person here who is at this specific location. I don't know if I'm trying to like I'm trying to make my point clear, but this is like how graph is being used, okay, in real world networks, like mostly in the case of, you can, if I give you the example of military, okay. So in the case of military, like maps, okay, like Google Maps, okay, or the internet allowing for complex path finding and relationship analysis. So for example, like in the case of military, if I give this example, they want to find the connection between two people, like where they are right now. So they will be like using a system on in whose the backend will be deployed this data structure graph. Okay, this is how it works. So next is the set data structures. Now set data structure is basically a collection of unique elements. Okay, that means that all of the elements, all of the values in it is are unique, in which the order of the elements is not significant. That means that the it doesn't matter what the order is. Okay, and the duplicate items are not allowed. This is one property of set data structures that is very like some people confused with other data structures, that the set data structures, they do not allow duplicate items. Okay, so for example, in the case of arrays, in the case of linked list, you would be like, you can use duplicate items, you can enter duplicate values. But if you are using the set data structure, it literally says collection of unique elements. Okay, so that means that all of the elements has to be different from each other. You cannot have duplicate items. Okay, and the order does not matter. So sets are primarily used for efficient membership testing, checking if an element exists. Okay, this is what why sets are used. Like you want to see, for example, some value exists in your program or not, you would use the set. Okay, if you want to remove duplicates, you would use sets, because sets do not allow duplicates. Okay, and performing standard mathematical set operations. We have studied set operations in like class 6, 7, and 8. If you guys have studied like union, intersection, difference. Okay, these are all mathematical set operations that set data structures use. Okay, so they are used for implementing indexes for fast data retrieval. Okay, and they do not allow to duplicate items, so that means that your data will only be containing unique and different values. Okay, and they are used for efficiently removing duplicate items from a list or array. Okay, so in a list, Python list, and in arrays, we can have duplicate values. But if you want to remove those duplicate values, you would use set. And for quickly checking if an item is part of a collection. So let's like look at this image here. Okay, this is how basically this is your array. Okay, and it's a not basically array but it's a set data structure, but looks like an array. Okay, and this is the begin. That means that from 5 this value your set is beginning, and in third on 30 this value it's ending. Okay, so if you were to implement this, like first of all, look at these values, they are not repeating. Okay, if they were repeating, it would not be a set. So these are not repeating. That means it's a set data structure, and here it's basically checking if the set is empty. Okay, so if the set is empty, it's not empty, that means it's equal to false. False is what? It's a boolean value. Okay, so is empty is equals to false. That means that your set is not empty, and is size, like it's asking for the size means the total number of values, so these are 6. So this is basically equal to 6 here. This is how he has implemented. Okay, and maximum size here, basically that this is the maximum size that you can store in a set data structure. So next one is the dictionary data structure. Dictionary, like in the last lecture, if you remember, we discussed some complex data types. And in those complex data types, we learned about those maps. Okay. And when I was talking about maps, I used the word key value pair. Okay. So in the dictionary data structure, it's an abstract data structure that stores collections of data as key value pairs. Okay. Like for example, name is key, and then value could be, suppose Alice name, key could be age, and value could be 13. So this is how dictionary data structures work. Okay, so this structure is also known by other names as a map, like how we saw in the last lecture. Hash map, in the case of like C++ language, these are called hash map. Okay, in Python these are called dictionaries, or associative array in various programming languages. Like concept is same, but in different programming languages these are known by different names. Okay, so do not get confused if you see these different like names there in different programming languages. Okay, like in Python these are called dictionaries, but in C++ these are called hash maps. The concept is the same, but their implementation is a little bit different. Okay, so dictionaries are ideal for situations where data needs to be accessed based on a specific unique identifier rather than an ordered position. So they are used for storing an object's properties, for example, a person's name, age, and address. Like how I gave the name example of name Alice, age 13, and address suppose Boulevard Street. Okay, or counting the frequency of items. For example, you can think write it as total number of apples 25. Okay, number of oranges 50. So such as words in a text document. So for example, like you are typing the words, the sentences in your MS Word or Google Docs, and those total number of words are 1500. Okay, so I can use the key value pair number of words equals 1500. Okay, now look, it works like this. Okay, this is the name of the dictionary. Okay, he has used, and this is how it looks like in because we're using programming languages, right? So we use these curly brackets first. Okay, and in those curly brackets we use the name sorry, key and key value pairs. Okay, this is the key. We use the key, we write the key in these quotation marks. Okay, then we use this thing Okay, I forgot the name here. Okay, and then we use the value here. Okay, so this is how it looks like, key value. So you write the key and values in quotation marks. Okay, and then use the separators here, use the commas here to separate the key value pairs. Okay, so Sarah, cheese, Lee, burgers, like this. This is how dictionary looks like. Okay, in Python, this is the example of a dictionary in Python language. In other languages it will look a little different. Okay, now we have covered almost all of the data structures and primitive and non-primitive data structures basically. Now if you look at the difference between linear and non-linear data structures, so in linear data structures we know data elements are arranged in what, sequential and linear order. Okay, so that means they're arranged in a sequence, and in non-linear they are arranged hierarchically or in a network, like you can see here trees and graphs, and we have examples here of linear data structures, arrays, linked list, stacks, and queries. So then data is accessed sequentially. That means data is accessed in a sequence. Random access is possible in arrays. Okay. And then in the case of non-linear data structures, data is accessed based on relationships or levels. Okay, and then traversal is linear. Traversal means that, for example, like in the case of array here, okay, you wanted to traverse to the end of the array. Suppose 9 is here, you wanted to find 9. Okay, so traversal is linear. Like this is how you will traverse. You will first look at this value. If it matches 9, uh, you will say no. Okay, then you will look at the next value. If it matches 9, for example, then next and next. When then until you find 9, you will find it, and then this is how basically traversing works. Okay, so start at one end. Okay, start from here and then follow through to the other end. In the case of linked list, stacks, and trees, it works the same. So in the case of non-linear data structures, traversal can be complex, such as depth first or breadth first in trees and graphs. These are some methods through we like traverse the elements in trees and graphs. Okay, then in memory allocation, so memory is generally allocated at compile time static. I already told that at runtime, if you try to change the size of, suppose, your array or stack or linked list, especially array, it will not work. Okay, you will get an error. Okay, so memory is allocated at runtime. Okay, but it's contiguous in memory. And then memory is allocated at runtime, often non-contiguously in the case of non-linear data structures. Okay, then next, if we look at here, insertion and deletion, simple operations like how you insert and delete into the linear and non-linear, but may involve shifting elements. Okay, so you can basically swap elements, he means. Okay, then in the case of non-linear data structures, insertion deletion can be complex. Okay, it depends on the position within the structure. Okay, because you need to balance out the trees and graphs. Okay, next, if you look at the use cases, so suitable for simple data storage and retrieval where data naturally forms a sequence. Why? Because these are sequential data structures. Okay, then non-linear data structures suitable for representing complex relationships. Okay, and hierarchical structures, like for example, they are used in maps and networking. Okay, and if okay, so we were looking at the difference between linear and non-linear data structures. So I was talking about use cases basically. In the case of linear data structures, like they are suitable for simple data storage. Like what are their uses? Just for simply storing the data, and retrieval where data naturally forms a sequence, right? But in like non-linear data structures, they are suitable for representing complex relationships and hierarchical structures, as we saw above in the case of trees and graphs. And then linear data structures, like their operations generally require shifting or linear traversal. Okay, like I showed you how you linear like traverse through an array or a stack, for example, which can be inefficient because you have to like traverse through one by one value and element to see if you have got your desired value or not, which can be a little time consuming. So in the case of nonlinear data structures, the efficiency depends on the type and complexity of the operations. Like suppose you're using trees instead of graphs. Okay, so it depends like type you're using and their complexity. Often optimized with algorithms like balancing or pathfinding. Then lastly, typically easier to implement and understand the linear data structures. They're easier to look at, implement in the case of like if you look at their code implementation using any programming language, they will be a little easier. But in the case of nonlinear data structure, they have really complex algorithms. Okay, it's like a maze. Okay, so you need to understand like where do you want to go in if you want to find this specific value in the tree or in the graph. So that was it. Then lastly, we will just look at the importance, okay, of understanding data types and data structures in programming. So why they are important and why they're fundamental to programming. Why? Because they allow, like both of these data types and data structures, they allow developers to write efficient, reliable, and optimized code. So choosing the right data structure and type for a given problem is crucial for managing data effectively and optimizing memory usage and ensuring correct operations. So first of all, if we look at the importance of data types, because we know what data types are, they like kind of like a variable, okay, a value kind of value a variable can hold, and the certain operations that can be performed. So they are memory efficient. That means that different data types require different amount of memory. If you remember in the last lecture, we looked at different data types like integer, boolean, and binary and character, all of that. And we looked how they are like how their size is different in different database management systems, right? So that means that different data types, they require different amount of memory. It depends what language you are using in the case of programming language, and what which like database management system, DBMS, you are using. So using the most appropriate compact data type, for example an 8-bit integer instead of a 32-bit integer if the range of values is small, optimizes memory usage, which is vital in memory constrained environments. Like in the case of like memory constrained environments, that means for example you want to like it's memory constrained. That means that you need to take care of memory. Okay, so you will use the 8-bit integer because its value is very small in the case of 32-bit integer, which is very large. Okay, the next importance is error prevention and type safety. So how like they prevent error. Data types help prevent errors by ensuring that operations are only performed on compatible data. Now, what does this mean, compatible data? Like in the case of integer, for example, you cannot use floating point numbers on integers. Like you cannot put the value of decimals, and you cannot store in integer variables. Okay, that would be incompatible. So this is how data types help you prevent errors. If you were trying to do that, your program would like give you an error, and you would have to change it. Then next is correct calculations and interpretation. So data types tell the computer how to interpret raw bits in memory, like if it's integer, if it's character, or suppose boolean, true or false. So it will tell the computer how to interpret that material. So without them, a program might confuse a date with a mathematical equation. Okay, now you will only store the date in the date data type, right? If you wanted to store date, you will use the date data type. But if you wanted to store, let's say, a mathematical equation, which one would you use? You would either use the string or the text, or like the math functions. They are in their functions, right? In programming languages, you would use them. Okay. So next one is code readability and maintainability. So explicit data types act as self-documentation. That means making code easier for other developers or your future self to understand the intended use of variables and functions. Next, if we see the importance of data structures, so we know what data structures are. They are built using primitive data types. Okay, data structures are built using primitive data types. So first one is the algorithmic efficiency. So basically, the choice of data structure, whichever data structure that you use, directly impacts the performance and efficiency of the algorithms that operate on the data. So suppose that you were trying to open a website on Google or any search engine, but that website is taking so much time to load. Now, what do you think would like be happening at the back end? There is like obviously some code that is happening and making the website lagging. It like its performance is not really fine. That means that at the back end of this website, some algorithm is in place. Like it is some algorithm is doing its work. But what about like this algorithm? It's kind of using some data structure, right? And if you are not using the right data structure, that algorithm would not work fine. Its performance would significantly affect your website, and it would not load properly. So for example, this was one example. Next is using a hash table for quick lookups. Now what's a hash table? If you remember, we looked at dictionaries. Okay, and dictionaries also have other names like hash maps, or like they have different names in different programming languages. So hash table is also is a table like key value pairs. Okay, so for quick lookups is significantly faster than using an unsorted array. That means that your array is not sorted, and in the hash table all of your values are sorted, so it will be easier for you to look up the data whichever you want using the hash table instead of the unsorted array for searching a large data set. Okay, then next is effective data management. So data structures provide logical ways to manage large amounts of data. So like how structures like trees are ideal for hierarchical data, like file systems, databases, while queues are excellent for task scheduling. In the case of operating systems, queues are mostly used, for example, printer queues, etc. And let's take the example of memory allocation as well. Then we have problem solving foundation. So understanding data, different data structures equips programmers with the right tools to tackle a wide variety of complex problems. So many real world problems inherently map to specific data structures. How the social networks as graphs, okay, undo features as tags, and there are so many other examples. Then last one, the importance of data structure is scalability. Appropriate data structures are essential for designing scalable systems. That means systems which you can grow with the time. Okay, and that can handle increasing amounts of data and users without significant performance degradation. So this is like the importance of data structures and data types. They have their own, each have their own uses, each has their own purpose, advantages, disadvantages, but they are used by different engineers, like software engineers, programmers across the world, and different applications which you use every day in your life.